Hello everyone, welcome to today's session. My name is Wycliffe, and in this video I want to share with you how you can obtain soil pH data for your farm or for your research activity or for any use you might want to apply soil pH. Now, soil pH is one of the most important indicators of soil health. It affects nutrient availability, root growth, and how well different crops can thrive. For example, some nutrients can only be available to plants at specific pH levels. Otherwise, they may be unavailable to the plant. Even if you apply fertilizer, your farm may not be performing well because the pH does not allow the nutrients to be available to the plant for absorption. So whether you are mapping farmland, running experiments, or monitoring environmental conditions, knowing the soil's pH helps you make better decisions for productivity and sustainability. So in today's video, I'll show you how to extract and visualize soil pH from the ISDA Soil Africa dataset. And we'll be doing that in Google Earth Engine, but we'll run that in R. For that, we will draw multiple polygons across different regions. I would think of drawing one around tea region, around sugarcane region, around rice region, and even the maize growing regions of Kenya. Now that I'm quite familiar with the country. Then we will pull some pH values from the polygons at two depths, like 0 to 20 centimeter, that is near the surface, and we will also obtain them at the second depth of 20 to 50 centimeters. Then we will reshape our results and create some clear comparisons across the three sites. But we can also do visualization of the whole pH. If you work with soils, GIS, or agricultural analytics, this workflow will be specifically useful or important for you, for your workflow. Okay, so let's jump in. Inside R, we'll start by loading rgee library and then initializing our session in Google Earth Engine. After that, we will also load some libraries that we will need, like ggplot, gg library ggplot2. We'll also need dplyr, as we will pivot some data. We will need tidyr to tidy the data. And then we will need sf to drop some geometries, and also map edit to digitize some polygons. Okay, so we already initialized our session, so let us draw the study sites or the polygons. And these, for your case, you might already have them as GeoJSON or GeoPackage, and you can just import it and convert it to Earth Engine object. So we will create some identifiers of these sites, and I will call them maybe sugarcane regions, sugarcane zone. We'll have tea zone. We'll have maybe rice zone, and lastly maize zone. Remember this you can do for even plots, small plots within each of these. Within sugarcane, you can have several plots and just check the pH within them, or any other boundary, whether you want to do it for a county or a district or a sub-county, whatever you want to do, you can do. Okay, so let's draw the polygons. I will have this ESRI, world imagery background, to help me draw this. And then in my list, I start with sugarcane. So I know this is a sugar belt. So I will generally draw a rectangle around that region. It doesn't matter the size for me now. And then the next one is tea. So I will go to tea growing region and drag another polygon. After tea and sugar, we have rice. So I know somewhere down here, they plant rice. These are rice farms. Somewhere here. And then lastly, we go to the maize farms. So maize farms are a bit far to the western region, this part. Okay. So let me have a look at my polygons. It seems the one for rice is a bit small. So I can increase its size by clicking this. And then I go to it, and then I can increase its size going this direction. So that's a rice growing region. Then I click save. So it's generally, they basically have almost the same size. Okay, so I have my polygons. Now what I need is the soil pH data. So soil pH will be from an Earth Engine image. And from dataset, we get a lot of image datasets available in Earth Engine. So I know it's from ISDA soil. Now there are so many variables under this, and they are so specific to Africa. So I call upon those who are interested in soil analysis in Africa, please, this is a very nice data set which you can easily interact with in Google Earth Engine and use. For example, you can get aluminum extractable, bedrock depth, bulk density, calcium extractable, carbon, organic carbon, total carbon, cation exchange capacity, clay content, iron extractable, magnesium extractable, nitrogen, pH, phosphorus. Just imagine the amount of data you can get here, including texture classes. So for now, I'm just going to work with pH. So I pick that. But as you can see, there is a lot of data you can see there. And if you want to look at what this data entails, then you can use EE-utils dataset display, and then you pass soil pH, and then it opens this interface or the Google Earth Engine catalog where the data rests. And then you can see the resolution of the dataset. It's 30 meters, so that's quite good for Africa. And there is description of the data, so you can read this, that the soil is available at 0 to 20 and 20 to 50 centimeters. So if you're looking for soil pH or soil data at greater depth than 50, then this may not be the right data set for you. Pixel values must be back transformed by dividing them by 10, right? So they are multiplied by 10 so that they are integers and they can be saved as int, because as float it will be taking a lot of memory. So it's just a good thing. Don't worry that these people are bothering you with division again once you have your data. Why don't they just save it the way you want it? That is to save memory. Nobody wants to waste memory or spend a lot of money getting more memory. So the dataset is available. Dataset availability is 2001 to 2017. It's not available on annual basis, but that is the period when data were obtained to train the models or to train the models that then were interpolated throughout the continent. You can read more about that in the description here and other papers related to this. Terms of use, citation. Of course, once you use this kind of data, you better cite them. But remember, this is not satellite image. This is an image product of some machine learning ensembling procedures. So there was some training that were done, and then interpolation or prediction was made throughout Africa. And now you have data you can work with. You are free to test this data with your ground truth, like go to the field, sample some pieces, some soils, composite them and take them to the lab, do your analysis, and then see how correlated the extracted values from this database align with what you obtain. Okay, so let's maybe first of all start by visualizing the map. So we can see the map by using visualization parameters, whereby we set maybe a minimum of maybe 30 or 35 and a maximum value of 105. Because the numbers are multiplied by 10, so uh, you know pH cannot be 35. pH ranges between 0 and 14. So we will use some colors here, and we will use hex color code so that we get more colors to work with. So we'll start with that color for red, and then the hash FFAA 00 is for orangish. And then we have the one that is becoming towards green, but not yet green, that is FF55. And then we can have 2B, hash 2B, and then FFD5. Okay, we are progressing towards, we can even end up with the blue, like 0055FF. If you are wondering where I'm getting these these colors from, they are all here. If you open this data catalog for ISDA, you will find the colors here. Okay, so those are the visualization parameters. Then we can display our map $add layer. And then the Earth Engine object is soil pH. And then because it has got several bands, if you go back here and check the bands, there are 4 bands. The first band is mean for 0 to 20 and mean for 20 to 50 is the second band. Then the rest are standard deviations. When you're using this kind of data, you are concerned about the standard deviation, yeah? And actually, they are indicating the minimum to be 35 and maximum to be 103. So, and the other one, the maximum is 102. So we already have some min max to use here. 35 and 102 or so, or 103. I mean, we can use 103 for both. So we will select one of the bands, and the band we are selecting for the first image is mean for 0 centimeters to 20 centimeter depth. After that, we provide the visualization parameters, and this we can just specify as the vis, which we have mentioned up there. So we can see the soil pH map for Africa. With the Congo forest having very low pH values, and as you go towards Sahara Desert, basically there is no record. There are no records, so it largely masked out, although some few records. Yeah. Then we can compare this with the map for, let's say the map for 20 to 50 centimeters depth. So that's simple. We just chain it here as 20 to 50. Same visualization parameters, but we use this bar to help us compare them better. Like we just drag around like this and we can see the differences, if any. Can we see any differences? Very, very, very slight differences. So let's make extraction around our region of interest, which are the 4 polygons. Okay, so we can say our pH data gets soil pH, and then we select We don't need the standard deviations for now. So we will just pick mean for 0 to 20, and then we also need mean for 20 to 50 centimeters depth, right? And then what we do to this is we reduce regions because we have a feature collection. And the collection, something is not right. We have soil pH, and then we select these, and then we reduce regions. That should be fine. So here we should have collection, and the collection is sites. And then we have a reducer, which is EE reducer mean, if we want the mean inside those. And then we can obtain them at the native scale of 30 meters. Seems something is not right. Man did new meet max. Okay, there is some man somewhere. This one, reducer mean. Okay. Yeah. So that is fine. So our pH data is Earth Engine feature collection, Earth Engine object feature collection. So we can bring that to an SF object by passing EE as SF, and then we pass the pH data as simple as such. Once we have it as SF, you can confirm that it's a simple feature with values for each depth and each site, and all of them are polygons. So this we can then use the convert it to a data frame by dropping the geometry. So it is pH, SF, and then ST drop geometry. That comes from SF package. All right, so we can make a data frame and pivot it and do all other things we want with it. PHDF. If we look at it, it is wide format, so we want to pivot it longer so that it's tidy, pivot longer, and the columns that we want to pivot are those that start with M. We can even say it starts with M, because they are the ones that have mean or something like that. And then where do names go? Names, we can take them to depth. And then values, that is the names here. This will be a depth, this will be a depth. And then the values under them will be pH. Okay. If we run this, we will see that we now have site ID and depth 1, depth 2, depth 1, depth 2, and the pH, corresponding pH value. And now you can confirm that the pH values are, of course, not what we expect for pH. They are way, way high. Higher than the standard because they were multiplied by 10. Okay, so we can then correct for those by dividing by 10. So we can mutate the pH and say it's the pH but divided by 10, kind of transmuting it. So if we run this, you will see the pH values here now being within the range of less than 10, most of them. pH not found. So what did we create? We created pH. Okay. So pH is pH divided by 10. Okay, so now they are less than 10. Here they were in more than 10 values scale. This is the scale we are told in the data set here that we need to correct them by dividing by 10, x over 10. After that, whatever you can decide to arrange the values by site ID, for example, and also by depth. So specific depth comes first and another depth follows. Okay, so that's what I wanted to show today. If you are interested in this or you find obtaining this useful for your case, then you can grab this code in the link I will leave in the description of this video and use it for your own case. As I said, it is not only soil pH that we have, but there are a lot of soil data. If you look for is that there are a lot of soil data specific for Africa that you can use if you want carbon, if you want bedrock depth, if you want nitrogen, total nitrogen, silt content, sand content, zinc, whatever you want. Basically, you will find it here specifically for Africa. Okay, remember to cite the data sets you use. If you use such kind of data, cite it accordingly. They provide even citation information here, so this should be recognized. And then the packages you use, also cite them accordingly. Thank you and happy coding. Bye-bye.